Breadth first search algorithm, commonly known as BFS. It is a fundamental algorithm in computer science, especially for solving problems related to graphs or trees. BFS is a graph traversal technique that starts at specified node, typically the root node, and explores all of its neighboring nodes. After visiting all the neighboring nodes, it moves to the nearest unvisited node and continues the exploration. BFS can be applied to any node in the graph, making it versatile for graph traversal. BFS is one of the most commonly used methods for graph traversal. It is a systematic approach that searches through all the vertices of the tree or graph. BFS classifies each node in the graph into two categories, visited and unvisited. It begins by selecting a starting node, then visits all the nodes adjacent to it, making them as visited, and proceeds to explore the neighbor of each node. Let's see the applications of BFS algorithm. The BFS algorithm has several applications, some of which include finding neighboring locations. BFS can be used to find all neighboring locations from a given starting point. Next is peer-to-peer networks. In peer-to-peer networks like BitTorrent or uTorrent, BFS is used to discover neighboring nodes such as seeds and peers in the network. Next is web crawlers. BFS is utilized by web crawlers to index web pages. It starts from a source page and follows all the links associated with it, treating each page as a node in the graph. Next is shortest path and minimum spanning tree. BFS helps to find the shortest path in unweighted graphs and can also be used for constructing a minimum spanning tree. The next one is garbage collection, that is also called Chinese technique. BFS is used in Chinese technique for duplicating garbage collection in programming languages with automatic memory management. Ford-Fulkerson method. BFS is a part of Ford-Fulkerson algorithm used to compute the maximum flow in flow network. Now let us see the algorithm steps. The steps for performing BFS on a graph are as follows. First, set the initial state. Set the status of each node in the graph G to 1, that is ready state. Next, enqueue the starting node. Add the starting node to the queue and set its status to 2, that is waiting state. Third, repeat until the queue is empty. Dequeue a node. Remove a node n from the front of the queue, process it and set its status to 3, that is processed state. Enqueue neighbors. Add all unvisited neighbors of node n, nodes with status 1 to the queue and set their status to 2, that is waiting state. 4. Exit. The traversal completes when the queue is empty. This algorithm ensures that all the nodes are visited level by level, starting from the root node and exploring all the neighbor nodes before moving to the next level. Now let's understand the working of BFS algorithm by using an example. Here you can see in the example, we have a directed graph having 7 vertices. In the graph, minimum path P can be found by using the BFS that will start from node A and end at node E. The algorithm uses two queues, namely Q1 and Q2. Q1 holds all the nodes that are to be processed, while Q2 holds all the nodes that are processed and deleted from the Q1. Now let's start by examining the graph starting from node A. Step 1. Add A to the Q1 and null to the Q2. Step 2. Now delete the node A from Q1 and add it into the Q2. Insert all neighbor nodes of node A to Q1. Step 2. Now delete node B from the Q1 and add it into the Q2. Insert all neighbor nodes of node B to Q1. Step 4. Now delete the node D from the Q1 and add it into the Q2. Insert all neighbors of node D to Q1. The only neighbor of node D is F. Since it is already inserted, so it will not be inserted again. Step 5. Delete node C from Q1 and add it into Q2. Insert all the neighbors of node C to Q1. Delete node F from Q1 and add it into Q2. Insert all neighbors of node F to Q1. Since all neighbors of node F are already present, we will not insert them again. Step 6. Delete node E from Q1 since all of its neighbors have already been added, so we will not insert them again. Now all the nodes are visited and the target node E is encountered into Q2. Complexity of BFS algorithm. Time complexity of BFS depends upon the data structure used to represent the graph. The time complexity of BFS algorithm is big O of V plus E. Since in the worst case BFS algorithm explores every node and edge in the graph, the number of vertices that is big O of V, whereas the number of edges that is big O of E, the space complexity of BFS can be expressed as big O of V, where V is the number of vertices.